and the transformation between different forms of energy on a macroscopic scale. Okay, so there are different laws of thermodynamics, out of which the very first law is the first law of thermodynamics. Okay, thermodynamics as a whole is governed by the laws of thermodynamics only. Thermodynamics as a whole is governed by laws of thermodynamics only. You need to have thermodynamics important laws. See, there are three laws of thermodynamics. The very first being the energy of a universe. Okay, the energy can neither be created nor be destroyed. It can only be transformed from one form to another. Energy, what is first law of thermodynamics? Energy can neither be created nor be destroyed. It can only be transformed from one form to another. However, the total energy content, the total energy content of a system is always remain constant. Is always remain constant. That is what first law of thermodynamics says. If you find out its mathematical expression, it is equal to delta E is equal to Q plus W. Q is what? Q is amount of heat. Amount of heat. And W is what? W is work done. W is work done. And what is mean by delta E? Delta E is a change in internal energy. You are seeing the delta there. Delta means E2 minus E1. Now we cannot calculate the absolute values of E1 and E2. We cannot calculate the absolute values of E1 and E2, but we can calculate their difference. We can calculate the difference between energy, internal energy of two different states. It could be final states and initial states. So that is why delta E is called as change in internal energy. Change in internal energy. Delta E is equal to Q plus W. If Q is positive, that means heat is absorbed. That means heat is absorbed. If your Q is negative, that means your heat is released. These are the conventions you really need to understand and remember also. What is mean by W? W is work done. If W is positive, work is done by the system. Work is done by the system. What is mean by system? System is that part of the universe which is under thermodynamic consideration, or it is that part of the universe which is getting investigated under the laws of thermodynamics. That is called as system. What is surrounding? Whatever remains after you considering a system, or rather I would say universe, total universe minus system is equal to surrounding. For example, suppose if you are observing the change in temperature or change in a phase in a small beaker, if you're considering it in a small beaker, then that beaker is your system, and whatever is outside the beaker is called as surrounding. Okay, so if the W is positive, work is done by the system. If your W is negative, then work is done on the system by surrounding. Okay, so these are some of the sign conventions that you need to remember for you to be able to solve the questions which comes afterwards. Okay, WREV. What is this WREV? WREV is work done in a reversible process. Work done in a reversible process. Work done in a reversible process is always maximum. And how much it is? It is minus 2.303 nRT log to the base 10 V2 by V1 or P1 by P2. It depends. It depends on different conditions. Okay, that is what the first law of thermodynamics and W max, maximum work done, is all about. Okay, moving ahead. second law of thermodynamics. The second law of thermodynamics, instead of putting it into words, let's understand its statement or equation only. It says that delta S total. What is delta S? This is entropy. Delta S is entropy. The second law basically says that total entropy of the universe is always increasing. Now delta S total is nothing but the entropy of the universe. If you observe the things around you, you will observe that entropy of the system is always increasing. And how do we measure the entropy? Entropy is the measurement of a disorder in the system. Entropy is the measure of a disorder in the system. Higher the disorder, higher is the entropy. Smaller is the disorder, more order the system, lesser is the entropy. Now, less order, that means what? If you keep anything for, like suppose if you're keeping a stone or I would say a rock for million billion years, the time will happen that as the time progresses ahead, you will observe that the rock gets decomposed. So I would say it is because of weathering, it is either getting decomposed or it is either getting converted into a soil. So that means what? Disorder in the rock has happened. So that disorder is what? Entropy. That is why if you observe everything around you, you will always see that disorder in every system is always increasing. That means entropy of the universe is always increasing. And what is entropy? Entropy of a universe or total entropy is equal to entropy of a system plus entropy of surrounding. That is what our second law of thermodynamics is all about. Okay, so moving ahead. Now, applications of thermodynamics. See, thermodynamics provides the relationship between heat, work, and measurable properties of matter. What are the measurable properties of matter? Enthalpy, entropy, internal energy, temperature, pressure, volume, Cp, Cv, all of these are measurable property. It can predict the direction of a natural change. It can predict the direction of natural change. For example, you know that delta G is equal to delta H minus T delta S. So if your delta G is negative, reaction is spontaneous. That means reaction is happening on its own in a nature. If delta G is positive, that means reaction is non-spontaneous. That means reaction is not happening on its own. You need to provide energy or you need to bring that reaction to. And if delta G is 0, that means reaction is at equilibrium. That we had seen in case of chemical equilibrium. Remember? Okay. So moving ahead. It predicts up to what extent a chemical reaction can proceed in forward direction. Now we know, we had seen that in case of Q, C and Kc. If Qc is smaller than Kc, that means reaction should go in a forward direction. If Qc is larger than Kc, that means reaction should go in a backward direction. And if Qc is equal to Kc, that means reaction is at equilibrium. Okay, so lastly, it helps in understanding why different phases of matter exist and provide a simple relationship between various measurable properties of system. Now you know all these things, right? There are some limitation. It doesn't tell anything about a rate of reaction. Thermodynamics doesn't tell you about a rate of reaction. Why? Because rate of reaction is being told by kinetics. Is being told by kinetics. And kinetics and thermodynamics, these two are large branches of physical chemistry. Okay. Lastly, it also doesn't tell about a path or mechanism. That is again being told by kinetics, because that's a different branch of physical chemistry. It has not been included into thermodynamics. We will be covering the questions from kinetics also in the upcoming sessions. Okay. So moving ahead. Thermodynamics. Now system. What is system? Which I have already told you, it's a part of the universe which is under investigation, is called system. Okay. Next, surrounding. Anything outside the system is called as surrounding. Okay. Now, there are different types of system: closed system, open system, isolated system, homogeneous system. What is mean by open system? In an open system, there is an exchange of heat and matter. Suppose if you keep the beaker like this, if you keep the beaker filled with the water, keep the beaker filled with the water. If you keep this on a table, if you keep this on a table, okay, and there is no lid over it, then this will be your open system. Why? Because here there will be exchange of matter as well as energy. Energy, because whatever amount of heat being radiated or being poured on this, that will make the temperature increase or decrease of this water. Suppose if the temperature is increasing, some part of water will starts getting converted into vapors, and in the form of vapors it will just escape. So that means energy has come here, energy has gone also. So both things can happen. That means there can be exchange of energy. Okay, that's the one thing. Second thing, there can be exchange of matter also. You can put the matter into it or you can take out the matter from it, which makes it a open system. Okay, then what is closed system? In a closed system, suppose if I keep the lid over it, suppose if I keep the lid over it, now this is your closed system. Now this is your closed system. Now there is an exchange of energy still. Whatever amount of radiation is being falling on this beaker, that will increase or decrease the temperature of water. It might convert water into vapors, or if the temperature is too low, it might convert the water into ice also. That means there is an exchange of heat here. Okay, there is exchange of heat, but there is no exchange of matter because you keep the lid over it. So you cannot take the water out of it. You can put the water into it. That is making it a closed system. Lastly, isolated system. What is meant by isolated system? Whenever there is no exchange of matter as well as energy. Whenever there is no exchange of matter as well as energy, it is called as isolated system. That means there is no exchange, matter as well as energy. For example, a tea or water kept in a thermos. Tea or water kept in a thermos would be called as isolated system. Okay. The next is homogeneous system. Homogeneous system is that system where both the phases or whatever number of phases are present there, all of them are in the same phase. So all of the substances which are present in the system, they are, all of them are in the homo, or then in the liquid system, or in the gas system, or in the solid system. If they are having a different phase, for example, solid, liquid, gas, then there will be called as heterogeneous system. Then boundary wall. There are different types of wall. Rigid wall. In rigid wall, there is no exchange of matter, but there is the exchange of energy. Non-rigid wall, there is the exchange of both the things. Adiabatic wall, there is no exchange of heat. That is called as adiabatic wall. Lastly, diathermic wall, there is no exchange, the wall which compasses so that there is no change in temperature. Okay, so these are kind of walls and types of system. Okay, so moving ahead. Example. The very first example, when no heat energy is allowed to enter or leave the system, when no heat energy is allowed or to enter or to leave the system, it is called as adiabatic process. In adiabatic process, no heat energy is allowed or to enter or to leave the system. Okay. Next, a system is changed from state A to state B by one path. That means here you have a state A. You are going from state A to state B by, suppose, by path number 1. This is one path. Okay. And then from B to A by another path. Now you're again going from B to A by another path. Let's consider that as path number 2. Okay. If delta E1 and delta E2 are the corresponding changes in internal energy, then see, internal energy is a state function. Internal energy is a state function. It's not a path function. That means it doesn't matter by which path you're going from A to B and which path do you follow from going B to A. Okay, that means path 1, path 2. If path 1 is delta E1, where you're going from the A to B, in path 2 you're going from B to A. That means it must be reverse of delta E1. So its value has to be negative. So if delta E1 is positive, your delta E2 has to be negative. And both of them should have same value. Suppose if delta E1 is 1, sorry, A, the delta E2 must be minus A. So therefore, if you add them together, delta E1 plus delta E2 is equal to A minus A. It has to be 0, because all of this is about internal energy, which is a state function. It depends on initial state, which is A, and final state, which is B. It does not depend on this path. And that is why our answer here has to be C, where addition of both of this corresponds to answer 0. Okay, chalo, moving ahead. Next, heat and work are two important path dependent quantities. We know that. Your heat is a path function. That means amount of heat absorbed by system or amount of heat released by system will always be dependent on what path you follow. It always dependent on what path you follow. Same is the work. Heat is Q, work is W. So W, that means work, is the amount of work done by the system or amount of work done on the system. Is always depends on the path that you follow. It, because you see, whenever you are having this delta, that means that whatever you have in front of delta, suppose let's keep delta X. Now your X could be E, making it delta E, then delta H, delta G. Whenever you are having delta G, all of these are state functions. State functions are the functions or are those thermodynamic quantities whose value depends on initial and final states of the system. It doesn't depend which path your system has followed. So whenever you see a delta there, it has to be a state function. If you do not have a delta, it may or may not be a path function. Okay, but more often than not, if you don't have a delta, it has to be a path function. For example, Q, which is heat, work, which is W. Okay. Now next. Now extensive property and intensive property. What's the difference between them? Extensive property are those property whose value is dependent on the amount of substance. Extensive property are those property whose value is dependent on the amount of matter present in the system. For example, mole. Now we know that amount of mole or value of mole is dependent on amount of matter present in the system, because amount of matter present in the system will decide if the number of moles are more or less. Okay. Similarly, mass. Mass is has to be extensive property. Mass will definitely change if you change the amount of substance in the system. So mass has to be extensive property. That's for sure. Lastly, heat absorbed. The amount of heat absorbed is dependent on amount of matter present in the system. Yeah, that's fine. The heat is the path function. It depends on what path your system is following. That's all fine. But amount of heat absorbed or amount of heat given is always dependent on how much matter is present in your system. Okay. Nextly, intensive property. See, intensive properties are those properties whose value is not dependent on amount of matter present in the system. Now let's talk about concentration. Now concentration is equal to mole by volume. Now look, mole is also extensive property. Volume is also extensive property. But their ratio which is concentration is a intensive property, is an intensive property. So always remember this, the ratio of extensive property is always an intensive property. What I'm saying, ratio of extensive property is always an intensive properties. The example is right in front of you. Concentration is a ratio of mole by volume. Mole is extensive property, volume is extensive property, but concentration is a intensive property. Similarly, density of a 1 gram of water and density of 100 gram of water, or density of a 1 liter of water at a given temperature is always same. And density is the ratio of mass by volume. Now we all knew that mass is the extensive property, volume is also extensive property, but the ratio, which is density, is intensive. Lastly, heat capacity. Heat capacity is equal to amount of heat absorbed by the system divided by rise in temperature. Now heat absorbed obviously is an extensive property, depends on amount of matter which is present in system divided by rise in temperature. That means by absorbing heat or by releasing heat, how much energy or how much temperature has increased or decreased. That is dividing heat absorbed will give you heat capacity. So heat absorbed is a extensive property. Rise in temperature is also extensive property, but heat capacity is a intensive property. Then temperature. Temperature is also a intensive property. Temperature of a 1 degree Celsius, sorry, temperature of a 1 gram water and temperature of a same water having 100 gram would always be same. Okay, that means temperature is also intensive property. So these are some of the general property: extensive, intensive, path function, state function. Okay, so moving ahead, I hope you must be enjoying the session. Thermodynamic equilibrium. Now thermodynamic equilibrium is what? It is the equilibrium state of the system in which the state variables are uniform and constant throughout the whole system. Now what are the state variables? For example, pressure is there, volume is there, temperature is there, and then they are going from P1 to P2, V2, P2. So if you write a delta P, P2 minus P1, if it is 0, delta V, V2 minus V1 is also 0, and delta T, T2 minus T1, if that is also 0. So if they are uniform or constant throughout the whole system, the system is said to be in a thermodynamic equilibrium, which is very rare to achieve. Okay, it's not something which can be achieved very easily. Okay, there are three types of equilibrium. The mechanical equilibrium. Mechanical equilibrium means there is no net change in position of the equilibrium. Mechanical equilibrium means there is no net change in the position of a system. That is called as mechanical equilibrium. Chemical equilibrium we had seen already in the last lecture. Thermal equilibrium. Thermal equilibrium is the equilibrium where temperature is not changing. Temperature is remaining constant. So that is how there are different types of equilibria. Okay, moving ahead. Next, equation of a state. Now, equation of a state that relates variables such as pressure, temperature, volume, and number of moles to each other. And we know what is the equation of a state. It is ideal gas equation. PV is equal to nRT. PV is equal to nRT. Okay, this ideal gas equation is the most celebrated and most enjoyed gas equation. Okay, but as the time was progressing, scientists observed that this ideal gas equation is not completely valid. It is valid only to a certain gases, and that too under certain conditions. It is applicable only to a certain gases, that too under certain conditions, and that is why it was eventually corrected. It was eventually corrected into this format, which is P plus A n square v square into v minus nb is equal to nRT. This is called as van der Waals equation of state. This is called as van der Waals equation of state, where your A is a corrected value, or I would say A is a correction factor in the value of pressure. A is a correction factor in the value of pressure. However, B is the correction factor in the value of volume. Okay, that is how the van der Waals corrected this ideal gas equation into this format. Okay, moving ahead. Process. What are thermodynamic processes? We know there are different types of thermodynamic processes. For example, isothermal. In isothermal, there is no change in a temperature. That means in isothermal, your delta T is equal to 0. Isobaric, the process which is happening, or the process which is being carried out at constant pressure. That means delta P is 0. The adiabatic process, the process which is being carried out at constant heat. The process which is being carried out at constant heat is called as adiabatic process. That means Q is equal to 0. Then isochoric process. Isochoric process, it is that process which is being carried out at constant volume. So therefore, delta V is equal to 0. And lastly, cyclic process. Cyclic process is that process where total work done is 0. So that is how these are different thermodynamic processes. Then these processes can be done by two ways. Either is reversible way, either is irreversible ways. We already know what reversible and irreversible processes are. Okay, moving ahead. What is a change in internal energy? What is the change in internal energy delta U for a system that does 70 joules of work and then absorb 45 joules? Now this question is based on our first law of thermodynamics, which is what? Which is delta U is equal to Q plus W. Okay. Now what they're saying, change in internal energy delta U for a system that does 70 joules of work and absorb 45 joules. Now absorb 45 joules, that means Q is positive. So you will write 45 here. Then system does, that means W has to be negative. If work is done on the system, your work done should have been positive. Here work is done. Oh, sorry, did I make a mistake here? Oh no, for a system that does 70 joules of work. Okay, so here work is not done on the system, work is done by the system, and whenever work is done by the system, its energy always decreases, which makes W negative. So 45 minus 70, making it minus 25 joule, and that is why our answer here has to be C, which is 25 joule. Okay, next. If the internal energy of an ideal gas decreases by the same amount as the work done by the system. Now we know work done by the system, that means your W has to be negative. And if the internal energy, which is delta U, if the internal energy of an ideal gas decreases by the same amount as the work done by the system, that means minus delta U has to be equal to minus W. Okay. Now on both the sides of the equation, you are having a negative sign. That means your delta U is equal to W. So delta U can only be equal to W if your Q is 0. You can see this equation, right? Delta U can only equal to W if Q is 0. So, but here delta U is coming equal to W. That means your Q has to be 0. And Q is 0 in which process? In a diabatic process. And that is why our answer here has to be C. Okay. Chalo, I hope you must have enjoyed this and understood it very well, thoroughly. Okay. Moving ahead. If you have any doubt, you can ask me in the comment section. internal energy does not include, internal energy does not include what? The internal energy includes everything that comes into it. That, see, what is the meaning of internal energy? Whatever you have inside the system, whatever you have inside the system is called as internal energy. Now, how many types of energies you have inside the matter? So inside the matter, your electrons are undergoing translational motion, electrons are undergoing rotational motion, electrons are undergoing, the electrons are being bound by the nuclear force, so nuclear energy is there. Electron or atoms are also vibrating in a system, so vibrational energy is there. Everything that is being encompassed into inside the matter, that is internal part of the matter, and whatever energy it encompasses, all those types of energies together are called as internal energy. That means vibrational energy is included into internal energy. Rotational energy, obviously it has to be included into internal energy. Nuclear energy, yes, nuclear energy is also included into internal energy. Only the last, energy arising by gravitational pull. Because whatever, suppose if your matter is present at suppose this height at this tower, and it will fall by the force of gravitational pull. Now that gravitational pull is external, right? It is external. So energy now coming into your matter will not have any consideration or will not have any connection with your internal energy. And that is why energy arising by gravitational pull will not be included into internal energy. Okay. So moving ahead, 2 moles 2 moles of an ideal monoatomic gas are allowed to expand. 2 moles of an ideal monoatomic gas are allowed to expand adiabatically and reversibly from 300 Kelvin to 200 Kelvin. The work done by the system is, now what is the formula for that? The delta, sorry, not delta, W is equal to NCV delta T. W is equal to NCV delta T. Now they have asked us what is the work done. Number of moles are how many? Number of moles are 2, right? CV is already being given 12.5 joule per Kelvin per mole, right? Let's write it joule per Kelvin per mole multiplied by delta T. What is delta T? T2 minus T1. T2 is 300, T1 is 200. We can see that. Rather, in fact, it's a reverse. It's a reverse. T2 is your T2 minus T1. T1 is 300, T2 is 200. So 200 minus 300, right? Now 2 into 12.5 is equal to how much? 25. 25 into minus 100. Sorry, minus 100 degree Kelvin. This Kelvin goes. So 25 into 100, it becomes how much? Minus 2500. Minus 2500 joule per mole. It is joule per mole. So joule per mole, you need to convert that into kilojoule. And we know that 1 kilojoule is equal to 10 raised to 3 joule. Or in other words, dividing whatever value you have in a joule by 1000 will give you your value in a kilojoule, which is minus 2.5 kilojoule per mole. And that is why our answer here has to be B, and it is B. Okay. So moving ahead with this now. The difference between heats of reaction, the difference between heat of reaction at constant pressure and heat of reaction at constant volume. Now we know that heat of a reaction is delta H, okay? But heat of reaction at constant pressure has to be equal to your delta H, right? And heat of reaction at constant volume becomes delta U. It becomes delta U. Okay. Then what's the relationship between them? See, delta H is equal to delta U plus delta NGRT. Delta NGRT. Where what is equal to delta NG? Delta Ng is number of moles of gaseous product, number of moles of gaseous products minus number of moles of gaseous reactant, that is equal to delta Ng. So they are asking the difference between delta H and delta U. That is what they are asked here, right? They asked the difference between heat of reaction at constant pressure, which is delta H, and heat of reaction at constant volume, which is delta U. So you can correct this. Delta H minus delta U is equal to delta NGR, right? Now, delta Ng. Now let's find out the number of moles. Delta Ng, number of moles of your product are how many? 12 in a gaseous form, right? This is in liquid state. We need to ignore this. Here also we need to ignore this. But we need to consider this 15 O2. That means 15 moles of oxygen. So 12 minus 15 is equal to minus 3. Your delta Ng is minus 3 multiplied by your R. Multiplied by your R, which is 8.314 joule per Kelvin per mole, right? R is joule per Kelvin per mole. And 3 is what? Mole. Mole per mole getting cancelled. And multiplied by temperature. Temperature is how much? 25 degrees Celsius. Making it 298 degree Kelvin, right? So 298 degree Kelvin. Degree Kelvin per Kelvin gets cancelled. Whatever answer we get, it must be in a joule. And then we need to convert that into kilojoule, because they have asked us the difference between them in kilojoule, right? Sure. So 298 into 8.314. We need to multiply this now. 0.34 into 298. Now obviously we don't know the table of 298. So 298 into 4. It must be 300 into 4 is 1200. 1200 minus 8. So it becomes what? 1192. Yes, 1192. 109. 298 into 1 plus 119. Go to 300, 417. 741. 298 into 3. 300 into 3, 900. 900. 894. 894 plus 41. 6. 935. You get the 5 here. 93. 298 into 8. 8 8 is 64 for 6. 8 9 is 72 plus 6 78. 7. 8 to the 16 plus 7 23. 2384 plus 93. 437. 9 plus 8 7. You got 1. 4. 2477. So 2477, then 3 decimal point 123, making it 2477.572. So 3 into 2477 into 572. Let's see how much it becomes. 2477. Let's take this simple digit into 3. 3 into 7 21 2. 3 into 7 21 plus 2 23 3 2. 3 into 4 12 plus 2 14 1. 3 into 2 6 plus 7. So it is 7 minus 7431 joule, right? Then how can we convert this into joule? Kilojoule. Divide this by 1000 and we will get minus 7.4 kilojoule, and that makes our answer to be A, and that is why A is the correct answer for this. Okay, this is how you can solve this numericals. Next, molar heat capacity. Molar heat capacity of water in equilibrium with ice at constant pressure is. Now, whenever your ice is getting converted to water, and whenever your water is getting converted to your ice, the total change in energy, or I would say dq, your dq is zero. dq is zero. So molar heat capacity, if you find out the molar heat capacity, what's the formula of molar heat capacity? The formula for molar heat capacity is dq by dt. Sorry, dq is not zero, dq is non-zero, dq by dt. See, what is the formula for molar heat capacity? Amount of heat absorbed or amount of heat released divided by total change in temperature. Now, whenever your water is getting converted to ice or ice is getting converted to water, and if they are in equilibrium, at equilibrium, in this case, there is no change in temperature. So, if there is no change in temperature, that means your delta T has to be equal to 0. Therefore, your C is equal to dq by 0, making it equal to infinite. And that is why the molar heat capacity in this case is infinity. Okay, that is how you can solve this kind of numericals. Okay, so moving ahead. Thermodynamics, a reaction has delta H is equal to minus 33 kilojoule, delta S minus 58 joule per Kelvin. This reaction would be what? Spontaneous and all that. We need to find that. Would this be spontaneous at all temperatures? Would this be non-spontaneous at all temperatures? Would this be spontaneous? Okay, let's find out. Delta G, what is the formula? How can we find out the spontaneity? By taking the Gibbs free energy. What is the Gibbs free energy? Delta G is equal to delta H minus T delta S. Now always remember this thing. Whenever you are considering delta H, delta G, the unit has to be same. You can see for delta H, I had taken 33 kilojoule, and for delta S, I had taken joule only. So either you convert joule into kilojoule or you convert kilojoule into joule. Let's convert kilojoule into joule. That will be rather easy. So delta H is 33 kg kilojoule. That means it is minus 33,000 joule minus T into delta S. How much is delta S? Minus 58 joule, right? Making it minus 33,000 minus plus 58 T. Okay, T is, we don't know what T is. So this is the equation that we have got for delta G. Now reaction can be spontaneous. Reaction can be spontaneous if your delta G is negative. Now delta G can only be negative if this value, which value? 58 into T. This value, if it goes beyond 33,000, then and then only your delta G can be negative. For example, let's take 58 into 600. 600, that means your temperature is a 600 Kelvin. Okay, let's see if it goes beyond 33,000 or not. 600 into 8 has to be 4,800. So 480. 6,000 into 5 is 3,000. 3,000 plus 480. 3,480. So that means 34,800. Yes, so it has gone beyond it. So 33,000 plus 34,800. So if you subtract this, it will have a positive value. So when it has a positive value, it will become a non-spontaneous. That means, sorry, by mad, this product 58 into T has to be lesser than 33,000. That means suppose if I take 500 degree Kelvin, temperature is in the 500, 58 into 500, 508 is what? 4,000? 0, 4, 0, 0. 500 into 5 is 2,500 plus 400, 2,900. So 29,000. So if this becomes 29,000, your delta G becomes negative. So 500 degree Kelvin around this. So it cannot be spontaneous at all temperature, right? You just saw that. When you take the temperature 600, it becomes non-spontaneous. If I take the temperature 500, it becomes spontaneous. So it has to be spontaneous above a certain temperature only or spontaneous below. Correct answer is D. It has to be spontaneous below a certain temperature. So 600 is surely there. 600 is surely there. So it has to be spontaneous below 600 temperature only. Okay. That is why the answer has to be D here. Okay. Chalo, moving ahead. Thermodynamics. Next question. Out of boiling point, entropy, pH, and EMF of a cell, how many of them are intensive properties? Boiling point, if you take 1 liter of water, if you take a half liter of water, that means 500 ml, or if you take 100 ml of water, all of them will have same boiling point. Your boiling point will never ever change. So it is not dependent on amount of matter present in the system. So it has to be intensive property always. So now one is present in every option. Okay. Second is pH. What is pH? pH is equal to negative. Let's forget this symbol. pH is equal to concentration of H plus ion. It is a concentration of H plus ion. And what is the formula for concentration? Concentration is number of moles upon volume. Now we had seen earlier that number of moles are extensive property. Volume is also extensive property, but their ratio, that means number of moles and volume, their ratio is concentration, which is intensive property. So if the concentration is intensive property, pH has to be intensive property. So 1 and 3 has to be intensive. That means 1 and 2 of the A option has gone. D option is still there, but let's see. Boiling point, pH, entropy. Entropy is what? Delta S. What is the formula for delta S? Delta S, the formula is, it is a Q reversible by temperature. Q reversible by temperature. Now again, Q reversible is what? Q reversible is extensive property. Temperature is also extensive property. And we knew that the ratio of two extensive property is always intensive property. And delta S is the ratio of Q reversible by temperature. That means delta S has to be intensive. Delta S is what? Entropy. That means 2 is also a intensive property. So boiling point, entropy, pH, all of them are intensive. Lastly, EMF of a cell. EMF, that means E0. Now you might know the formula delta G is equal to minus NFE cell. So E cell is your EMF. So E cell is equal to delta G upon NF. So you are having N, which is number of moles, F, Faraday. These are extensive property. Okay, but delta G is not extensive. Delta G is intensive. So that means E cell is not a extensive property. Sorry, it is not intensive property. It is extensive property. It depends on amount of matter present in the system. And that is why our correct answer is 1, 2, and 3, which makes the option B correct. Okay. Next, which has maximum internal energy at 298 Kelvin? That means helium gas, oxygen gas, and O3 gas. Out of these three, if we keep the temperature same, which is 298, so out of these three, which would have the maximum internal energy? Now remember always, if you are keeping the temperature constant for the given number of system which is having more number of atoms per molecule, the system which is having more number of atoms per molecule will be having the highest internal energy. And in our question, O3 is having a 3 atoms per molecule, and that is why your O3 will be, the O3 will be having a highest internal energy. Okay, so moving ahead. 1 mole of ideal gas is allowed to expand reversibly and adiabatically from a temperature of 27 degrees Celsius if the work done by the gas in the process is 3 kilojoule. What is the final temperature? 1 mole of ideal gas is allowed to expand reversibly and adiabatically from a temperature of 27 degrees Celsius to what? That means T2. We need to find that T2. If the work done by the gas in the process is 3 kilojoule. Now, what was our formula? We used this relation earlier also, where W is equal to NCV delta T, which is equal to NCV. What is delta T? T2 minus T. Okay. So NCV, N is 1 here. Okay. W is 3 kilojoule. So 3 kilojoule, that means we need to convert that into joule. That is making it 3000 joule. And CV. CV, they have given 20 joule. And T2 minus T1. Now T2 minus T1, out of that, we know the T1, right? T1 is how much? 27. So in Kelvin, it becomes 300 degree Kelvin. So how can we solve this now? And see, let's bring this 20 joule on that side. So 3000 divided by 20 is equal to delta T. 0, 0 gets cancelled. So delta T is equal to 300 divided by 2, which is 150. The difference of delta T between two temperature is 150. Okay, and T2 minus T1. T2 minus 300 degree Kelvin is equal to 150. So therefore T2 is equal to 150 plus 300, which makes T2 to be equal to 450 degree Kelvin. So 450 minus 300 is equal to 150, right? That means delta T is 150 and T2 is 450 degree Kelvin, which makes answer B to be correct. That is why answer is B here in this case. Okay, that's how you can solve such questions. Moving ahead, cyclic process is shown in the process. Cyclic process is shown in the process. PT diagram is being shown here. So if you look at this process, they ask which of the curves shown the same process on VT diagram. So here we have a PT diagram and here we have a VT diagram. They are saying the process that we're looking at the PT diagram, out of that, these all so out of the 4 processes which we have seen here, which corresponds to this. Okay, now let's solve it one by one. So if you look at this process, the pressure is on the y-axis, T is on the x-axis. So when you're going from A to B, your pressure is increasing. Pressure is increasing. When pressure increases, volume decreases. And when the pressure is increasing, temperature is increasing. When the temperature is increasing, volume should increase. So pressure increasing, because of which volume is decreasing, and since the temperature is increasing, volume is also increasing. So in one process volume is decreasing, in another process volume is decreasing. So therefore both of this cancels out each other, making your volume change is 0. So it is isochoric process. Now A, B is basically, A going to B is isochoric, because temperature is changing, pressure is changing. I can't say isothermal or isobaric. So it is isochoric process, that's for sure. But temperature is heating, no? So you can say isochoric process or isochoric heating. You can say isochoric heating. Okay, next, B to C. When you're going from B to C, you can see The temperature delta T is equal to 0 now. B to C temperature is constant, right? So when the temperature is constant, let's look at the pressure also. Pressure is decreasing now. The pressure is decreasing. So delta P is decreasing, but the temperature is constant. So it is isothermal, right? But when the pressure is decreasing, volume should increase. So when pressure is decreasing, volume should increase. And whenever volume is increasing, what do we call that as? Expansion, right? But it is happening at constant temperature. So what do we call B to C? Isothermal expansion. It is called as isothermal expansion. Okay. Next. Lastly, A to C. When your system is going from A to C, you can see that the change in pressure is zero now. Change in pressure is zero. Pressure is constant. But the temperature is what? Temperature is increasing. Your temperature is increasing. So when the pressure is constant, volume naturally has to be constant. Delta V is also zero. But temperature is increasing. So what do we call this process as? Isothermal process, no? It is isothermal process. Okay, sure. So now let's see out of these four which corresponds this. Okay, first if you look at the AB, in AB volume is increasing and temperature is decreasing. Sorry, temperature is constant. Here delta T is 0 but volume is increasing. So volume is increasing but temperature is constant. What do we call that as? Isothermal expansion. So here AB is isothermal expansion. But if you look at our original diagram, the BC was isothermal expansion, right? That means this cannot be our corresponding graph. Okay. Next, the B. If you look at the B, AB, what is AB? In AB, temperature is decreasing. In the AB, temperature is, I made a mistake here. In the third process, they're not going from A to C. They're actually going from C to A. Sorry, my bad. We went from A to B, B to C. That I made it correct. Lastly, we are going from C to A. Now C to A, delta P is constant, delta V is constant, but C is what? C to A, going temperature is decreasing. So it's a cooling. It is not isothermal actually. It's a cooling. You can call that as adiabatic cooling because there is no change in a volume and pressure. Okay, it's a cooling. So now look at here. In AB, volume is constant. Okay, that means it's an isochoric process. A to B, sorry, it's a B to A. And then you got what? When you are going from A to C is actually isochoric process. Oh, sorry, my bad, man. Look at the process again. When you're going from B to A, your delta V here is 0. But temperature is what? Temperature is increasing. So your B to A is isothermal, isochoric heating, which was A to B in our case. But here it's B to A. That means it cannot be the correct also. If you look at the C, when you're going from A to B, volume is constant, but T is increasing. That means A to B here has to be isochoric heating. So A to B was isochoric heating here also. And A to B is isochoric heating here also. Okay, that is for A to B. Now B to C what? B to C was isothermal expansion. Isothermal expansion. Now look at here B to C. When you're going from B to C, temperature is constant, but volume is increasing. That means B to C is also isothermal expansion here. So, and C to A, if you look at C to A temperature is getting constant. Sorry, temperature is decreasing. As the temperature is decreasing, volume should also decrease. That means it's a cooling process. Therefore, the diagram C corresponds to our answer. That is why our answer is C here. Okay, this was a bit challenging question. I know this kind of question may take some time. but this kind of question may ask in the exam. Okay, sure. Moving ahead. Thermodynamics. Now, for a monoatomic gas, the value of the ratio of CPM and CVM is, okay. Now, for a monoatomic gas, we know that CV is equal to 3 by 2 R. For a monoatomic gas, CV is equal to 3 by 2 R. Okay. And Cp minus Cv is equal to 3 by 2 R. That means not 3 by 2, R only. Cp minus Cv is equal to R. Therefore, Cp is equal to Cv plus R. So, what is value of Cv? This 3 by 2 R plus R, making value of Cp to be equal to 2R, 5 by 2 R. And they have asked us the ratio of Cp by Cv, which is gamma. Gamma is equal to Cp by Cv, which is equal to 5 by 2 R divided by Cv, which is 3 by 2 R. Therefore, 5 by 2 R into 2 by 3 R. R gets cancelled, 2 gets cancelled, is equal to 5 by 3, which is equal to 5 as to 3. And that is why our answer is 5 by 3. Okay, that's how you can solve it for the monoatomic gas. Okay, sure. Moving ahead. Which of the following equation represents a reaction that provides the heat of formation? Which of the following equation represents a reaction that provides heat of formation of ethane? Now, how do we form ethane? See, ethane, you have a CH3 minus CH3. Okay. Now, whenever you see a formation of any compound, you need to take the standard states of the substance. Now, what is the standard states for carbon? Standard state for carbon is the solid state. Okay. So, solid state of carbon plus 6 hydrogen are there. The 6 hydrogen, that means you cannot take 6H. 6H is a dissociated form of a hydrogen gas. It is not the standard form of hydrogen. That is why we need to take 3H2. We need to take 3H2, yes, because there are 6 hydrogen now, to give us CH3. That is our ethane gas. And that is why the correct answer has to be B here. The correct answer has to be B. Okay, sure. Moving ahead. Thermochemistry. Now we are into thermochemistry. Thermodynamics actually is a compartmentalized into 2 sectors: thermodynamics and thermochemistry. Thermodynamics is including all those basic concepts of thermodynamics, and thermochemistry is all about the reactions, the formation of a substance, and their heat related questions. Okay, basically Hess law. So the heat of formation of CO2 and H2 are given. Using the data for following combustion reaction, calculate the heat of formation of C3H8. Now, if you look at the heat of formation of the C3H8, or I would say a normal heat, this is standard heat of formation of this reaction. The standard heat of formation of this reaction has to be equal to heat of formation of CO2. Okay, there are 3 CO2, therefore into 3 plus water is in the liquid state, pure state, so we don't need to consider it. Okay, so product minus reactant, basically heat of reaction is equal to heat of formation of product minus heat of formation of a reactant. That is how we solve this. So product is our CO2. Okay, that is what we have got here, minus reactant. The reactant is your oxygen. Oh, sorry, in this case they are given for the water also, no? Sorry, my bad. So delta H0 is 3 into heat of formation of CO2 plus heat of formation of water, which are 4. 4 into delta HF formation of water, that is your complete product side. Now reactant side, minus heat of formation of C3H8. That is what our equation has to be here. Now delta H0 is already given, right? Minus 2221.6 kilojoule, that is equal to 3 into formation of CO2. CO2 is 394. So 394 into 3, 3 into 4, 12, 2, 1, 27 plus 1, 28, 8, 2, 3 into 3, 9 plus 2, 11. So you got 1182 plus 4 into H2O. How much is for H2O? Minus 285.8 into 4. 4 into 8, 32, 2, 3. 4 into 5, 20 plus 3, 23, 3, 2. 4 into 8, 32, 32 plus 2, 34, 4, 3. 4 into 2, 8, 8 plus 3, 11. So 1143.2, that is our complete product side, minus delta HF for C3H8. Now obviously we need to solve that. Now we need to add this and send it to the right hand side, left hand side, sorry. So 1182 plus 1143.2. So 0.2325, 8 plus 4, 12, 2, 1, 3, 2325.2. Sending it to the left hand side, what do we get? Minus 2221.6 kilojoule, and this is also in kilojoule, minus 2225.2 kilojoule is equal to minus delta HF C3H8. Okay, what do we get now? I think we had gone to some, okay, let's 400, just a sec. Okay, let me take some CO2 into 3, H2O into 4, all of them have got added product. Oh, it was a minus here, sorry, my bad, it was a minus here. Yeah, it was a minus, and delta HF formation is that we need to calculate. Minus, this was plus, delta H was already given, so, and this was, oh, this was minus, no, sorry, this was minus 1182 minus 1143. Both of them were minus, so this is minus 2225.2, which goes on the left hand side to make it positive. Yeah, now it gets subtracted. So 2225.2 minus 2221.6. So 2 divided by 6, it become how? 6. Yeah, 1. You got 3, 0, 1, 0. 200. So 103.6. Yes, that is the answer. So, but it is minus. So it is minus 103.6 kilojoule, and that is makes our answer D, minus 103.6 kilojoule. Okay, chalo, moving ahead. The heat of formation of CO2 and H2O are minus 394 kilojoule per mole and minus 285.8 kilojoule per mole respectively. Using the data for the following combustion reaction, calculate the heat of formation of C2H2. Now again, CO2 and H2O are given. Okay, we need to find that for the C2H2. How can we do that? Again, delta HO is equal to heat of formation of CO2 plus heat of formation of H2O minus heat of formation of C2H2. Okay, now this is a pure substance. For pure substance, heat of formation is equal to, for pure substance, heat of formation are always equal to 0. Okay, CO2, H2O, these are not pure, no, they are made up of two elements. This is pure element, no, O2. Okay, so 4 into CO2 minus 394 into 4, 4, 4, 16, 6, 1, 4, 9 are 36 plus 1, 37, 7, 3, 4, 3, 12 plus 3, 15, 1, 5, 7, 6. So minus 1, 5, 7, 6. That is 4. Then for H2, it's 2, right? So minus 285.8 into 2. 2 into 8, 16, 6, 1. 2 into 5, 10 plus 1, 11, 1. 2, 8 is 16 plus 1, 17. You got 1. 2 2s are 4 plus 1. 571.6. That is also minus 571.6. That is our product side. Then on the reactant side, you got what? This minus formation of C2H2. Formation of C2H2 we need to find out. So delta H formation of C2H2. Delta H 0 is given, minus 2601 is equal to minus 1576 plus 571.6. 0.6, 6 plus 1, 7, 7 plus 7, 14, you got 1, 5 plus 5 is 10 plus 1, 11, 1, 1 plus 1, 2, 2400, so 2147.6, that is minus delta HF C2H2. So sending this to that side, minus 2601 plus 2147.6 is equal to minus delta HF of C2H2. Okay, so basically we are subtracting now. From 2601 we are subtracting 2147.6. Here you go to 0. 0 minus 6, 4, 1, 7 plus 1, 8, 10 divided by 8, 2, 1, 10 minus 5, 5, 1, 6 by 6 minus 2, 4, 2 minus 2, 0, 452.4, but that's a minus because the larger number has a negative sign, making it minus 452.4 is equal to minus formation of C2H2. 452, I think we made a mistake here again. 2600, this is 15 plus 7, 2100, making it somewhere closer to minus plus 452. No, it is right. 394 into 4. No, nothing is wrong. So minus sign gets cancelled. So heat of formation of C2H2 here is 452.4 kilojoule. Now we don't have that option here. That might be a mistake. Some mistake, we don't know what it is. Okay. But it has to be 452.4 joule. It must be just somewhere this. Okay, this is 200, but there might be 400 there. So that is how we can solve this numerical of a chemistry. Okay, moving ahead. Next, using the following data, calculate the heat of formation of C2CH4. Now we can again calculate this on the basis of the previous cases only. So we know the heat of formation of the whole process is 890.4 is equal to CO2 plus H2O minus CH4. So CO2 is minus 393.5 plus water 285.9 into 2. 2 into 9, 8. 1. 2 into 5, 10 plus 1. 2 into 5, 10 plus 1, 11. 1. 2 into 8, 16 plus 1, 17. You got 1. 2 into 2, 4 plus 1, 5. So 571.8. But for water, it's also negative. Minus 571.8. That minus you have a heat of formation of CH4. Yeah. So this minus minus it becomes positive. So 393.5 plus 571.8. 8 plus 5, 13, 3, 1. 3 plus 2, 5. 9 plus 7, 16, 6, 1. 5 plus 4, 9. So 965.8. We got 890.4 is equal to minus 965.3 minus heat of formation of CH4, that is methane. Sending this on that side, 890.40 plus 965.3 is equal to minus heat of formation of CH4. So plus minus minus. So 965.30 minus 890.40. So we can see it is somewhere close to 74.9. We can see clearly that 003490 1 5 minus 1 4 6 minus 9 16 minus 9 7 1 9 minus 9 0. So 74.90. So it is plus 74.90 is equal to minus heat of formation of CH4. Now heat of formation, changing the side of sign, delta HFCH4 is equal to minus 74.90 because you have a minus here. And that is why our answer came out to be minus 74.90. Okay, and that's it for thermochemistry and thermodynamics. Okay, we are finishing the session here, but if you want to see more of such content, if you want us to bring more and more of such content, please like our channel, like this video. Please subscribe to our channel, which is practically live on YouTube. You can also log in to our practically off app, which is present on Play Store. It is also present on App Store. You can download it from there. You can log into it. You can check it out. We have interesting courses. We have courses in Vedic maths, robotics. Okay, we have interesting courses in Vedic maths, robotics, then coding. You will really enjoy it. We have a simulation based model, AI based model, which will help you understand your given concept from whatever board you are belonging to: CBSC, CBSC board, IGCSC board, ICSC board, or your state board. It will help you understand the concept from all the boards. We have brought all of that on our Practically app. You can please log into it, and you can like our channel on YouTube, which is Practically Live. Okay, thank you. This is Mayur More signing off. Okay, let's meet in the next lecture.